In this chapter, we have been leveraging information about the derivative to inform us about the function. We started off with looking at graphs of derivatives to try to figure out what the function looks like whose derivative was given. And we most recently also talked about local linearity or local linearization, where we leveraged information about the tangent line and the slope of the tangent line to give us an approximate value for a function. So what we're going to do, and we're going to try to start to formally work out this process. And essentially what we're doing is we are taking the derivative and trying to come up with the function who gives us that derivative, that gives us that derivative. And this process is called anti-differentiation. It's a process of determining a possible function whose derivative is known. And we're going to start discussing some actual rules for this, but before we do that, let's actually just kind of see if we can come up with some ideas just by observing a couple of functions. So look at this first row here. So consider this first row. Let's just go through them and let's see if we can just quickly identify all the derivatives of these functions. Well, we know that the derivative of sine x minus 2 is just going to be cosine x, because the derivative of that negative 2 is 0. Number 2, what is the derivative of that? Well, it would also be cosine x. Number 3, cosine x. Number 4, also cosine x. Hopefully you're noticing a pattern. Number 5, with no constant, still cosine x. So clearly we see here for all of these functions, they have the same derivative cosine x. So then if I said that the derivative is cosine x, what would you say that the function is? What is f of x? F of x would clearly have to be then some function sine x plus any type of constant, which we'll just label as plus c. It just could be any constant. We notice in all of these examples here, we had a bunch of different kinds of constants, and it didn't really matter what they were. Every single time, the derivative of a constant is just 0. To really hammer this home, let's look at the next line. So consider these functions here. What would be the derivative of 3x to the 5th minus 2? Well, it would be, applying the power rule, f prime of x would be equal to 15x to the 4th. And the derivative of negative 2 is just 0. What about for number 2? Also 15x to the 4th, and the derivative of 11 is just 0. Again, I'm not going to belabor this too much. You get the idea. As we go along, the derivative of all of these functions, despite the different constants, is always 15x to the 4th. So then if I gave you that derivative, what would you say that f of x is? F of x would have to then be 15x to the 4th, again, plus, excuse me, not 15x to the 4th, 3x to the 5th, I apologize, 3x to the 5th plus some constant c. So we're kind of informally doing this. We're just doing this by observation, but you get kind of start to get the idea, and a really important idea, that here, because the derivative of any constant is always 0, when I'm coming up with the antiderivative, or the function whose derivative is given to us, it should be clear that we can come up with any plus possible constant. And that's an important idea, because what we're effectively saying here is when we're coming up with an antiderivative, we're finding a family, and I'll write this, we're finding a family of functions. That is to say, we're coming up with a function plus an infinite number of possible vertical shifts here, and an infinite number of possible constants, because when I take the derivative of that constant, it's just going to be 0 anyway. So when we're finding an antiderivative, we're finding a family of functions. So to continue on with just kind of observing a process here, let me just quickly try a few of these before we get into some formal rules. If I gave you the derivative of 3x squared, ask yourself, can I think in reverse or do this process in reverse and come up with the function whose derivative is 3x squared? Well, I know that my coefficient, when I take the derivative, I'm going to take my power and I'm going to multiply it by my coefficient. So if my coefficient of my derivative is 3, that means my power must have been 3. And that makes sense because I had to decrement this power of 3 to get it to become 2. Well, what about something like f prime of x? Here for number 2. Well, we know that this is equivalent to x to the negative third. So the same way, f of x would have to be equal to x to the negative 2. And since I ended up with a coefficient of 1, that means this had to have been negative 1/2. That's the only way that when I take the derivative of this, I would have ended up with 1 as my coefficient and my power being -3. Continuing on, the derivative, if the derivative is negative sign, that means my original function must have been cosine x. If the derivative was 1, which function gives me a derivative of 1? Well, that had to be x. And pause the video and try the fourth one on your own, just kind of informally thinking through it. This would be f of x is equal to x cubed over 3 plus x squared over 2 plus x. Now look at all of these that I've done and ask yourself, am I missing anything important? And the answer is a resounding yes. With all of these, I could be adding some constant, and I should be adding this plus c here to indicate that we could have taken the derivative of this function with any constant and ended up with what we had here. So be very careful, and it's important to add that plus c whenever we're finding an antiderivative. Now, fortunately for us, when we're finding antiderivatives, we don't really just have to do this kind of backwards thinking process all the time. There are, fortunately for us, a set of rules that allow us to find antiderivatives pretty efficiently. Before I talk about these rules, let's make sure that we understand that another name for finding an antiderivative is finding what we call an indefinite integral. And there's actually a big typo here. Apologize about that. That should say an indefinite integral. We'll talk about definite integrals in the next unit. But what we're effectively doing is to find an indefinite integral. It's just another name for an antiderivative. It's to find the family of functions whose derivative is known. What does a notation for an integral look like? Well, this symbol here is just telling us to integrate. And that symbol there tells us to integrate. Whatever we are integrating, this is known as the integrand. And finally, this dx here is simply telling us what variable we are integrating with respect to. So in this case, we're integrating with respect to x. This doesn't have any particular math effect. So don't think of it necessarily as multiplying by anything. It is simply letting us know what variable we are integrating it with respect to. So when you see that symbol, we're told that we need to integrate our integrand, and we're doing it with respect to this x. Okay? And the result is going to be a family of functions. And again, in the next unit, we'll talk about how to find what we call definite integrals. All right. So with that said, let's now look at some of the rules for integrating or finding antiderivatives. So probably the classic one is to understand the power rule. Because when we learned about the power rule for differentiation, let's say, for example, x to the n, what did we do? If this was our function, x to the n, we took that power, we multiplied it by our coefficient, and then we decremented it. Well, work in reverse order. Again, what did we do in the past? We multiplied by the coefficient, then we decremented the power. If we do the opposite or the reverse flow of that, we are going to add or increment to the power. So we're going to go from n to n plus 1. And instead of multiplying, we are going to divide now by that incremented power. We're just doing the reverse order of what we did before. Okay? So let me actually just jump to a quick power rule example. Let's look at this first one here. What if we said find the integral of x cubed dx? So to find the integral, we're going to take that power of 3, we're going to increment it. So 3 plus 1 becomes 4. And then we're going to divide everything by that power of 4. And then add that constant c. So the integral, or the indefinite integral of this is x cubed. The integral of x cubed is x to the 4th over 4 plus c. Because if I take the derivative of this, what am I now doing? I'm going to do the power rule, or maybe I should write it as 1/4. This might make it a little bit easier. If I were to differentiate this, I would take that power, multiply by the coefficient, so 4 times 1 over 4. Then I'm going to decrement that power. The derivative of any constant is 0, and this would just give us x cubed, which is exactly what we had initially. Okay? Some of the other rules for integrating, the constant rule here, this is simply letting us know that when we have a constant, the integral of any constant is always going to be the variable that you're integrating it with respect to, and that makes sense. If you were integrating, for example, 1, well, 1 is equivalent to x to the 0. Well, that would then, if I integrate this then, this is x to the 1 over 1, and that's equal to x. And again, what is the derivative of just x or any variable? A linear variable would just be 1, or in that case. So if I had this was 4, for example, let's just change this now to 4. This would then be 4x. That's the constant. Okay. All right. So actually, I'll just write 4x here, just so we get that plus c. Forgot about that. My bad. And then the scalar rule here, which is to indicate that if we have a scalar, we can always just kind of move that to the outside and integrate f prime of x or integrand first, and then just multiply our integral by k later on. Okay. And also in the same way that we had rules for trigonometric differentiation, really just the opposite of these are going to be, opposite of those rules are going to be our integral rules using trigonometry. So for example, if we know that the derivative of sine is equal to cosine, that means the integral of cosine x dx would equal sine x plus c. So just be a little careful about some of the signs there. When I say sign, I mean literally like the positive and negative signs, not so much the sine function, but just be careful about those. But those are some of the trigonometric rules. Now, there are more rules for integrating, which we'll cover throughout this course. We have things like integration by parts and sum and difference rules, but we'll take that one step at a time. These are just some basic rules to get us going with integrating for now. Here, we already did one practice problem. Let's just try one or two more just to really make sure that we have these. Let me try something like, let me make this a little bit smaller so we have some space to work with. Let me try something like number 5 real quick. Now, at first glance, you're seeing a quotient and you're thinking to yourself, oh, maybe we want to apply some kind of quotient rule for integration. Well, actually, there is no quotient rule for integration. There are certain product rules, but we can actually avoid that completely. Always ask yourself, if I'm having a hard time integrating, can I rewrite my integrand in some way? And we see here that we can actually rewrite this as cosine x over sine x times 1 over sine x dx. And cosine x over sine x can be rewritten as cotangent x times cosecant x dx. Now, you might be thinking we need to apply some kind of product rule here, but we're not there yet. Go back to your list of trig function rules and ask yourself, does that look familiar at all? And the answer is yeah. It would be this particular one right over here. So we're going to say this has then have to be equal to negative cosecant x plus c. Okay? Let's try something like number 9 here. Let's give this one a go. Pause the video and see if you can attempt that. Well, first thing I'm going to write, make sure we understand that this is the same thing as 3x to the negative 2 minus x to the negative 1/2 dx. And be kind of careful with the parentheses. I probably should do that. But as long as you have the dx at the end, oftentimes it's implied that you're integrating that entire integrand. Well, if I write it this way, then we can really just integrate each term. So if I'm going to increment x to the negative 2 power, this would be x to the negative 1. And then I'm going to divide everything by negative 1, so that would be negative 3. X to the negative 1/2, I'm going to increment that, so that becomes x to the 1/2. And if I divide everything by 1/2, negative 1 divided by 1/2 is just negative 2 plus c. So you can write your answer this way. You could also, if you want to, write this in radical form or rational form. Same deal. Okay. And let's just try one more together. Let's try something like number 10 here. We can see that this is going to be x to the 1/2 plus 1, if I just write this as rational exponents, times x to the negative 2 power times dx. Because again, right now we don't have any quotient rules. There aren't any. So we'd have to rewrite the integrand. What does this allow us to do? This allows us to distribute that x to the negative 2 and write this as x to the negative 3/2 plus x to the negative 2, all of this dx. And again, now we can integrate each term. This would be x to the negative 1/2, divide everything by x to the negative 1/2, so that would give us a coefficient of negative 2. X to the negative third, or excuse me, negative 1, I'm incrementing here. Divide everything by negative 1, so actually that would just be minus x to the negative 1, all of that plus c. You can leave it as that, or you can also write it as this. Neither one is any more correct than the other. Okay? And again, in the future, we will start looking at more problems where we have to find what's called definite integrals, or the specific function that exactly gives us that derivative. But as kind of an introduction to this, we'll look at some initial condition problems right now, where if we're looking at particle motion, if we know a point, for example, on f of x, then we can solve for the exact constant that we need for the given conditions. So this is kind of our first jump into finding the exact function given some specific conditions. So if we look, for example, and we see that f prime of x is equal to x to the negative third power, and we know that that function is going to go through the point 1, 3/2, right? This gives us the coordinate 1, 3/2. Now we can't say that we have a family of functions. We have a specific function that goes through that point. So let's start by integrating x to the negative third. If I integrate this, this is x to the negative 2 over negative 2 plus some constant c, okay? This is our function here. Well, I know that my function has to go through this coordinate, so I'm now going to solve for the c value such that this is going to be the case. So I know my y is 3/2. I know my x is 1. So solve for c. Well, this is just going to be 3/2 is equal to 1 to the negative 2. That put that down in the denominator. That's negative 1/2 plus c. And let me actually continue this right over here. If I add 1/2 to both sides, I get 2 is equal to c. So I can say now my function is x to the negative 2 over negative 2 plus the constant c. I found the specific constant, the specific curve, or the specific function, such that it will go through the point 1 over 3 over 2. 1, 3 over 2. And this is often used with problems involving position, velocity, acceleration, because we know that the derivative of velocity, for example, is acceleration. So if we're given an acceleration function, we can find the velocity function and find that constant of what we say the constant of integration. So let me try one practice problem with this. Let's try number 12 here. Given the acceleration of the particle at time t, if we're given the acceleration function as such, and we know what the velocity is at t is equal to 1, and we know what the position is at t is equal to 2, then let's determine the equation for the position of the particle. So we got to kind of move up the ladder, if you will. So if we're given the acceleration function, let's find the velocity function. So the velocity function is going to be the integral of a of t dt. So if we integrate that function, we can say v of t would then be t squared, divide 4 by 2, so that's going to be 2, minus the integral of negative 3, which is going to be negative 3t, plus some constant. Now that we have our velocity function, let's plug in what we know to solve for c. And we're going to say that our y value is equal to 6, our t value is equal to 1, and we can say here that since 6 is equal to negative 1 plus c, c is equal to 7, okay? Now, let's use that information to come up with our position function. So we know that the position function is the integral of our velocity function. So we're going to integrate 2t, what do we say v of t was? 2t squared minus 3t plus now here plus 7, all of that dt. And if we integrate this, we're going to go through that now. That will give us S of t is equal to 2 over 3t cubed minus 3 halves t squared plus 7t plus some constant. Now, I've got to be pretty careful here because right now I'm using the same constant of integration. And that's a big no-no because I can't then plug in that value of c into both of those equations or both of those functions and have it be true. So I'm going to need to label this something else. Something to really help out is if you know you're going to have multiple constants of integration, is to just go ahead and label this c sub 1 from the get-go, and let's call this c sub 2 because it's a different constant. So now that I plug in there, I'm going to say, all right, my y value is equal to 5, and I'm going to plug in 2/3 times 2 cubed, which is 8, 2 squared, which is 4, plus 7 times 2, plus this constant 2. Okay, and looks like I need a little bit more space to work with, so I'm going to shrink this stuff just to give myself some more room. Let's actually move this stuff down here. And this now, I can just move over. Okay, so I can say c sub 2, after you've done a bit of simplifying there, is going to be negative 25 over 3. So that's our second constant of integration. That was the constant of integration for our position function. So now we can put it all together. S of t is equal to 2/3 t cubed minus, let me just actually go in here, 3 halves t squared plus 7t, and it was minus 25 over 3. Okay? And that wraps up Unit 3. Go ahead and try these other problems down here. Oops, looks like it crashed here. But go ahead and try these other practice problems below. And if you have any questions, feel free to leave a comment or question in the comments below.